This video is for page 18 of your interactive notebook about the Bohr model of the atom. As you saw in the flame test lab, matter can absorb energy and then re-release that energy as light. However, much like you saw and scientists discovered, each element only produces a pattern of light with very specific wavelengths, and we call this an emission spectrum. In class, we also talked about the example of hydrogen gas, and this is an illustration of a glass tube in which I have a sample of hydrogen gas, and the tube is hooked up to a power source so that I can run an electrical current through this sample of hydrogen gas. And when the power source is turned on and electrical energy is put into this tube, you'll notice that the tube glows purple. Now the light that's emitted from this, if we put it through a prism and split it, splits into a band, or four specific bands, four specific wavelengths of light. One at 410 nanometers, one at 434 nanometers, one at 486, and one at 656 nanometers. And this pattern of wavelengths is known as the emission spectrum of hydrogen. This is unique for hydrogen. In fact, an emission spectrum is unique for its element. It's like a fingerprint. No two elements will ever have exactly the same emission spectrum. No two elements will produce exactly the same wavelengths of light whenever they're excited by absorbing energy. Back on the right side of your notebook, Niels Bohr was a scientist in the early 20th century who proposed that electrons occupied orbits with specific energy levels, and in part this was a way of making sense of this phenomenon. He also had a problem with the Rutherford model because the Rutherford model posited that we had negative electrons orbiting a positively charged nucleus. However, Bohr was concerned because since positive and negative charges attract one another, he reasoned that, according to the Rutherford model, the electrons should just spiral into the nucleus as they were attracted by the positive charge. So his idea was that electrons weren't just in orbit around the nucleus, but that they occupied a specific energy level, and that the amount of energy each electron had was sufficient to keep it moving around the nucleus. But based on the emission spectrums of different elements, he also reasoned that electrons could change energy levels by absorbing energy, but only in specific amounts called quanta. This is the plural of quantum, which we discussed on page 15 of your interactive notebook when we talked about electromagnetic radiation. And a quantum is a specific amount of energy. And it turns out that an atom can only absorb energy in very specific amounts, and it has to be exactly the right amount of energy for an electron to move from one energy level to another. Electrons can't move in between energy levels. They can only move from the first to the second, or the second to the third, or even from the first to the third. But they have to absorb a specific amount of energy. When an electron is in its lowest energy level, we say that it's in its ground state. And this doesn't have to be the lowest energy level in the atom, it just has to be the lowest normal energy level for that electron. Electrons that absorb energy and jump to higher levels are in an excited state. And of course, electrons can always return to the ground state from the excited state by giving off the excess energy as light. And this is emitted as photons. Remember that photons are the small massless particles that make up light. This process of electrons absorbing energy in quanta and releasing it is known as a quantum leap. On the left side of your notebook, in the Bohr foldable, we have a diagram of this process. So this diagram is split into two parts. The first part shows an electron in the second energy level absorbing energy from a photon that comes into the atom. And when it does so, it gets elevated to the third energy level. This would be its excited state. So the ground state was the second level, but the excited state was the third. Down here we have another electron that's in the third energy level that's now returning to its ground state, the first energy level, by giving off the extra energy as a photon. And whatever the energy of this photon is, which will be equal to the amount of energy, or the difference in energy between the third and first energy levels, can be used to determine the wavelength and frequency of the light, which is of course what determines its energy, or what determines its color. And this is how we get the emission spectrums for elements, right? So each time that an electron goes from one energy level to another, it's going to give off a particular wavelength of light that corresponds to the amount of energy that it's losing. Back on the right side of your notebook, specifically Niels Bohr's atomic model had a positively charged nucleus in the center that's made of protons and neutrons. And really, remember that the neutron was not discovered for a few years after Bohr first posited this theory, but eventually it gets incorporated into the model. And then around this positively charged nucleus, we have electrons orbiting, but again in specific energy levels. And we identify energy levels by the number n. So for example, n equals 1 would be the first energy level, n equals 2 would be the second, etc. If we fold that foldable back over to the front of it, then we have an illustration of the Bohr atomic model, and we're going to label that the center part is the nucleus made of protons and neutrons. We need to draw in a few electrons in the orbit around that nucleus, and then label them electrons orbiting, but again in specific energy levels. The last thing is that we can actually do calculations using this relationship between energy and Planck's constant and frequency of the photon. So on the left side of this, I have some data from a from a sample of hydrogen. So the values that you're given here are the values of the first 3 energy levels of hydrogen. So n equals 1, the energy is 2.176 times 10 to the negative 18th joules, and then it gives you the values for 2 and 3. And I have 2 questions here. The first is how much energy must an electron in the second energy level absorb to jump to the third energy level? And to solve this, which would be the change in energy, or delta E, we're just going to find the difference between those 2 amounts of energy. When we do that, it comes out to 3.022 times 10 to the negative 19th joules. That's the amount of energy that electron would have to absorb. The second question talks specifically about the emission of light when it returns to the ground state. So what would be the wavelength of the light emitted when the electron dropped back down to the second energy level? And there's a reminder that in order to convert from meters to nanometers, you can multiply your answer by this very large number, 1 times 10 to the 9th. So the change in energy is equal to Planck's constant times frequency. Now, you'll remember that we actually used this equation on page 15 of your notebook to calculate the energy of a wave. It works out the same. So the energy of the photon that's being emitted when this electron drops from the third energy level to the second is going to be equal to Planck's constant times the frequency. So if we know the change in energy, which we calculated above, then we can plug this into the formula to calculate frequency, which turns out to be 4.561 times 10 to the 14th hertz. Then we can use the relationship between wavelength frequency and the speed of light to calculate the wavelength, which comes out to 6.58 times 10 to the negative 7th meters. If we multiply this times 1 times 10 to the 9th to convert it into nanometers, we get 658 nanometers. And you'll remember maybe that 658 nanometers is roughly similar to this value right here. So this is going to be a red light. In fact, it's quite possible that the problem is alluding to an electron in the third energy level of hydrogen dropping back down to the second. So that's an example of how we can determine the energy of the photon and the wavelength and the frequency, whichever one we're given. So that's it for page 18 of your interactive notebook on the Bohr model of the atom.